In the last lecture, we talked about how every permutation of Sn it can be written as a product of two cycles. And remember last time we said that it doesn't have to be disjoint, so sometimes it isn't. There is something that is composition into two cycles. We also said, or we're going to show right now, that is not unique either. Now, it's not disjoint because that's what we showed the last time. We gave examples where you have this composition into two cycles is not disjoint, and that composition is not unique either. So in the following sense, let me look at this example here. So let me take a permutation in S5, so it's a permutation of the elements 1 through 5. So this is going to be this permutation here. 1 goes to 2, 2 goes to 3, and so on. Now, if you look at this composition that we have here, you can double check that this permutation right here is actually equal to this. Now, let me double check, for example, number 1 here. So 1 is mapped into 2. So what happens to this one? Now, remember, you start always from this side. So 1 is mapped into 5, and now 5 is mapped into 2, and then 2 gets fixed. So 1 is mapped into 2. So it's the same thing happening here. You can check the same thing for the other ones. 2 will map into 3, 3 to 4, 4 to 5, and 5 to 1. That will all happen in the same way here. So you will hold the same thing is going to happen. Now, this is a decomposition into two cycles. They are not disjoint because, of course, they share the number 5. And it's 4 of them. 1, 2, 3, 4. 4 two cycles. Now, this same permutation, you can write it in this way. This one right here. Now, you can also double check that. You can double check that this permutation here, and remember, this is a bijective function, is exactly the same as this permutation that you have here. So this is also a composition or product of two cycles, but in this case, there are 6 of them. So you see here that this composition into two cycles is not unique. So in this case, you have this composition is 4 of them, and then this one is 6. Now, even though it's not unique, there is a part of this decomposition that does not change. And that part that does not change is the parity of the number of two cycles. If you look at the example we had here, this is a product of 4 two cycles, and this is a product of 6 cycles. So these 4 and 6 are both even numbers. If you have a permutation that can be expressed as a product of an odd number of two cycles, then any other decomposition has to be also into odd number of two cycles. So that was one of the ideas we're going to talk about in this lecture. So before we do anything, I'm going to look at this lemma, and the lemma is the following. The identity of Sn is an even permutation. So what the lemma says this. So basically this here. So you have E here denotes the identity of Sn. Remember here, the identity of Sn is the function, the bijection that fixes all the elements from 1 through n. That's the identity here. Remember that Sn is a collection of functions. Now, if you happen to have the identity, it is a composition or product of alpha 1 through alpha r, where those alphas are two cycles, then this r here has to be even, meaning that 1, 2, 3, we have r two cycles. That's an even number of two cycles. So the identity is even. Every time you have the identity expressed as a product of two cycles, the number of two cycles is always even. Now, I'm not going to do the proof of this. The proof of this is by mathematical induction, and you can check it in the book. It's not that complicated, but is something that I don't want to go over. Now, that is for the identity. The theorem that actually I want to prove here is this theorem that always even or always odd. And so let's see what that means. So suppose you have a permutation alpha in Sn. So that is a bijection, of course. And then you have the permutation, the same permutation alpha is expressed as a product of two cycles in this way, beta 1, beta 2 up to beta r. And the same for, you have this order decomposition, gamma 1, gamma 2, gamma s. So two different there's composition into two cycles, which we know it could happen. Both of these alphas and gammas are, all of these things are two cycles. So if you happen to have the same function here, bijection, permutation, into product of two cycles, the number of two cycles, they might not be the same, but they have the same parity. So what that means is R and S, which is the number of two cycles here, and S is the number of two cycles here, both of those are either both even or both of them are odd. Alright, so I'm going to prove that, and this will always prove that whenever you have a permutation alpha and it's expressed as a product of two cycles, the number of two cycles here, the parity will be the same. So it's always even or always odd. So if this is, for example, 4, this composition needs to be an even number. And then if you have, for example, 7 cycles here, then this composition here has to be an odd number of two cycles. So let's look at the proof. So let's assume, of course, that then you have the same permutation alpha that is written in two ways, betas and gammas, and these are two cycles. All of them are two cycles. And we need to prove that R and S have the same parity. All right, so let's look at the proof. So we assume this. So of course, this composition here is exactly the same as that one. So we can write it down as this. Beta 1, beta 2 up to beta R is all this product of gamma. So basically those two things are the same. Now in the next step, because these two things are the same, one thing that I can do is I can multiply, it's not really a multiplication, but it's a composition by beta inverse here on the left. So imagine that I multiply here by beta 1 inverse and beta 1 inverse. Beta 1 inverse here is going to cancel out with beta 1. So I'm going to get beta 2 to beta R, and then beta 1 inverse is going to be here. So that's the reason right here. Now let's do that again. So I'm going to multiply or make the composition of here beta 2 inverse. So if I look at the beta 2 inverse here on this side and on this side here, the beta 2 inverse on this side is going to disappear. It's going to give me beta 3 through beta R. And the beta 2 inverse is going to be right here on this position, which is this one right here. Now, if you continue this way, if you keep multiplying on the left here by beta 3, beta 4, up to beta R, then on this side, you're going to, of course, get the identity. And on this side, you will get this product here. So you see the gamma 1, gamma 2, gamma S are all here, beta 1 inverse, beta 2 inverse, and so on until you get to the last one. So the identity is all of this. Now, for each one of these inverses that is here, beta 1 inverse, beta 2 inverse, all of them are two cycles. Every time you have a two cycle and you get the inverse of a two cycle, you get exactly the same two cycle. Why? Because think about what the inverse of a two cycle is. So the inverse of a two cycle is the inverse of the function that takes a to b and b to a. Now if you reverse that, then b goes to a and a goes to b. It's exactly the same as you have here. So if you have a function that maps a into b and b into a, then when you reverse it, b goes into a and a goes into b, which is exactly the same thing here. So every time you take the inverse of a two cycle, you get exactly the same two cycles. So all of these things that are here, beta 1 inverse is just beta 1 again. So I can go ahead and replace all of these things here that are inverse by just the cycles themselves. So this is beta R minus 1, and so on. Now, if you look at this here, this expression, this is a two-cycle decomposition of the identity. This is the number, and also one more thing is how many two cycles are here. Now, for the gammas, there are S two cycles, and for the betas here are R two cycles. So there is a total of R plus S two cycles here. So there's X two cycles here and R two cycles here. So the total is R plus S. Now remember, by the lemma, whenever you have the identity and it's expressed as a two-cycle decomposition, that has to be even. So by the lemma, R plus S is even. Now, if R plus S is even, remember that these are integers. So R plus S is even. That only happens if both of them are even or both of them are odd. For example, 3 and 7, they're both odd, but you get even. So whenever a sum is even, these two have to be both even or both odd. Why? Because if you get, for example, this R is even and this is odd, then the result will be odd, but that doesn't match with this statement. So both R and S are even or both R and S are odd. So we prove our theorem that says every permutation, when you express it as a product of two cycles, the number of those two cycles is always even or is always odd. So that proves the theorem. Now that's an important fact that we're going to use later to describe a little bit more properties of the permutations. So let's look at this definition. Even and odd permutation. So if we have a permutation alpha in Sn, we say that permutation is even if it can be expressed as a product of a number of even two cycles, and the same for odd. Now this definition that is here will not make sense if you can take a permutation and express it as an even number of two cycles and as an odd number of two cycles. The definition will not make sense if we have that, but by the theorem, this definition will make sense, because whenever you have a permutation, is always a product of even number of two cycles or odd number of two cycles. So this definition will make sense here. So a permutation is always even or is always odd, depending on the number of two cycles in which you can decompose it. All right, so let's see an example. Let's see how you check that something is even or odd. So let's look at this two permutations here. So we have the permutation alpha and beta, and the alpha is represented by this array notation, and the beta is represented by this array notation. We want to check whether this is even or odd and beta is even or odd. Now, one thing you might want to do this is, instead of having the array representation, you want to have the cycle representation of this. So the cycle representation for alpha, remember this means 1 goes to 3, 1 goes to 3, and then 3 goes to 4, and then 4 goes to 2, and then 2 goes to 1, which is the one that is here. So this alpha is represented by this 4 cycle here. The 5 is ignored, remember, because it's fixed. Now, we saw in an earlier lecture how we express a cycle of any length, of length bigger than or equal to 2, as a product of two cycles. Well, basically what you do is you take this element here, 1, and match it with this one. So it's 1, 2, 1, 4, 1, 3, 1, 2, 1, 4, 1, 3. So if you check this permutation here, it's exactly the same as this one. That means this permutation alpha that we have here is an odd permutation because it's a product of two cycles, so 1, 2, 3. So that alpha will be odd. The same thing we're going to do with the beta here. So we express beta in a cycle form first. So here 1 goes to 3, 3 goes to 2, 2 goes to 1, which is this one here. And the 4 and the 5, both of them are fixed. We ignore them here in the representation. So we can express that using the same idea here. So how do we express this in product of two cycles? So it's 1, 2, 1, 3. So that's what we have here. So this is a product of two cycles. So that means that beta is an even permutation. All right. Now, one more thing that I want to do here is look at this theorem. So there's because we can get a subgroup of the total group of permutation of n elements using the even permutation. So the theorem says this: even permutations form a group or a subgroup of the total group of permutations. So let's see the statement. So the statement says the set of even permutations, and that should be a plural there, the set of even permutations in Sn and the collection of all the permutations forms a subgroup of Sn. Now remember, in Sn, when you have a permutation, it's either even or odd, depending on how many 2 cycles can be that can be decomposed in. Okay, so let's look at the proof. Now we're gonna use a little bit of notation here. So we're gonna denote by A sub n the set of all even permutations in Sn. So out of all the even permutations in Sn, we're gonna collect them all in one set that we're gonna call An. So if we do that formally, that means An is the collection of alphas in Sn, so alpha is even. Now, we want to prove that An is a subgroup of Sn. Remember, this less than or equal sign means subgroup. So An is a subgroup of Sn. To do this, we're going to use one of the theorems we saw earlier in the class, which is we use the two-step subgroup test to check that a subset is a subgroup of a certain group. Now, let me recall what that is. So the two-step subgroup test means there are 2 things I need to check. Actually, there's 3 of them. The first one is that it's a subset. So the set that you are claiming is a subgroup needs to be a subset first of the whole group. And that subset cannot be empty. So it has to be different from the empty set. The second part is this. Every time you take 2 elements in the set An, then alpha, and this is star here, the binary operation. In this case, the binary operation is composition, but I'm ignoring that here. So alpha beta inverse is also in An. So once we check that these 2 things are true, then we will have proof that An is a subgroup of Sn. So that's what we're going to do. So let's go into the proof of part A, which is this part here. Now, to check that An is a subset of Sn, that's not going to be difficult because the only thing you have to do is look at the definition. So let's look at the definition of An. So what is An here? An is, by definition, all the alphas that are in Sn, so alpha is even. So in particular, the elements of An are already elements of Sn. So that proves that An is already a subset of Sn. So that proves this part of part A. And the next part is to prove that An is not empty. Usually, when you want to do this, you check that the identity is here. That's usually how you do it. It doesn't have to be, but the identity is usually the one that you use to check that the set is non-empty. And that's what we're going to do here. Now, by the lemma that we mentioned already, that is proved by mathematical induction, by the lemma, we know that the identity is even. So the identity of Sn is even. Because it's even, An contains all the even elements of Sn. So that means the identity is in An. So An is not empty. So that's part A. So that proves the first part here. That's part A. Now let's look at the second part. So let's look at that part. So for part B, so let's assume then, because it's an if-then statement, let me go back here. It's an if-then, it's an if-then statement. So I'm assuming that alpha and beta are in An, and we're going to prove that alpha product with beta inverse or composition here is also in An. So let's assume that alpha and beta are in An. Now, what does it mean to be an An? An An means that you are even permutation. So that means that when I take my alpha, I can express it as a product of 2 cycles, and the number of 2 cycles here is even. So here in this case, I have R cycles, so that R has to be even. For beta is the same thing. Something is an An if beta is a product of an even product of 2 cycles. So all the lambdas that are here, so that is S of them, they are 2 cycles, and then S here is even. So that's the number of 2 cycles we had for beta. We have to prove that alpha beta inverse is a product of even cycles. And if we prove that, then we will prove that it's an An. So let's look at what this is. So what is alpha composed with beta inverse? Now alpha is right here, so I'm going to replace it by the gammas, and beta I'm going to replace it by the lambdas. So this is the gammas here, and this is the lambdas. So the gammas of course stay the same here. Now remember, when you take the inverse of a composition here of functions, then it reverses the order. So lambda s is the last now, lambda s inverse will be first one, and so on. So this, when you take the inverse, always reverses the order of the operations here. So it's lambda s inverse, lambda s minus 1 inverse, and so on until the lambda 1 inverse, that is the last one. Now remember what I mentioned in this lecture. Whenever you take the inverse of a 2-cycle, and these are 2 cycles, all these lambdas here are 2 cycles, that is exactly the same thing. Now, because the inverse of a 2-cycle is always the same thing, as I explained earlier. So lambda s inverse is lambda s, and lambda s minus 1 inverse is the same thing, lambda s minus 1, and so on. Now, so what we have here is this expression that is here, this product of gammas and this product of lambdas, that is a 2-cycle decomposition of alpha beta inverse. But how many 2 cycles we have here? So we have R cycles here for the gammas, and we have S cycles here for the lambdas. So what that means is that alpha beta inverse is the product of R plus S 2 cycles, and both R and S are even because alpha and beta both were an AS. Remember, R and S are both even. So the addition of 2 even naturals is an even natural. So that means that alpha beta inverse is a product of even 2 cycles. That shows that AN is a subset of Sn. So not only that, it's a subgroup of Sn. So the collection of all the even permutations of Sn is a subgroup of Sn. So that's all I have to say for this lecture. And the next lecture we will see some examples about this subgroup of Sn. So let's see some particular examples about the An. And one more thing I want to say is this. If you try to do this with the odd permutations, so let's say you have a collection of the odd permutations, so let's call it Bn here. So if we call Bn the collection of all the elements in Sn so that alpha is odd, that collection is a subset of Bn but is not a subgroup. You can think of one of reason here is the identity is not even here because the identity is even. So this is not a subgroup already. It's also not closed. If you take 2 odd permutations and you combine them together, you do the composition. If it is odd and odd, you get even. So Bn is not closed. So the collection of all odd permutations is not a subgroup, but the collection of even permutations is a subgroup. All right. So that's all I have to say for today. Take care and good luck.